Okay, good morning to everyone, and thank you, Francesco. Thank you for the invitation to the organizers. It's great to have this opportunity. So I'm going to tell you about experimental observations of solar neutrinos from the PP chain to the CNO cycle. So as you know, the fundamental paradigm here is that the sun is producing a huge amount of electroneutrinos through this process by turning hydrogen into helium. This takes place by means of two set of reactions known as PP chain and CNO bicycle. So the PP chain is this set of reactions, which I'm not going to discuss in detail because there will be a talk by Francesco Villante later today. In any case, as you can see, I have highlighted the processes which are producing electroneutrinos. So these are well-known processes in terms of particle physics, so we can predict the energy spectrum of each of these produced electroneutrino. In addition, there are different so-called terminations in this PP chain with different probabilities. So the largest case is when you produce two helium-3 nuclei which are producing helium-4. However, there is another process which was introduced independently long time ago, between 1937 and 39 by von Weizsäcker and Bethe, taking into account that in second generation stars there is some carbon and nitrogen in the core of the star, and this can give rise to the same fundamental process, turning hydrogen into helium. And actually, as a matter of fact, this was taught since till, I think, 1950s, the most important process for producing energy in stars. And this is the so-called CNO cycle. I don't know, it's stuck. Which is highlighted in this slide. So when you start by producing nitrogen 13 on carbon 12, and then nitrogen 13 decays beta, producing an electron-neutrino. Also in this case, we know very well the energy spectrum of this electron neutrino. And then oxygen 15 is produced, and there is a beta decay of oxygen 15. Then at some point in this process, you can produce, in the most of the cases, carbon 12, and then start again the same set of reactions, or oxygen 16. If you produce oxygen 16 with a low probability, then you end up to another branch of this cycle, and put all together, this is the so-called bicycle, CNO bicycle, which operates at low temperature in quote, in stars. So in the end, this is what we predict, that the energy production in stars is due to these two processes, PP chain and CNO cycle, that there is, because of conservation of energy, a strict relationship between the energy produced from the star in terms of electromagnetic radiation and the neutrino production at the core of the star, that this changes as a function of energy, the production rate, and for the sun, the dominant process is due to PP chain. By far, and more details will be given later by Francesco Villante. But the question is, can we probe this idea through solar neutrino observations? So this is the question that I'd like to answer. So this is the energy spectrum of solar neutrinos. The most important point I'd like to underline here is that the most of the solar neutrino flux by far is below 1 MeV. This is important from an experimental point of view. So the most of the solar neutrinos are sub-MeV particles. So coming to detection, These are the interaction channels which have been taken into account over the last about 60 years. So electron capture, this is a charged current which produces in the final state a nucleus which can be radioactive. And in fact, one can observe the radioactivity of this nucleus. In that case, we speak about a radiochemical observation. Or an electron in the final state, and one can observe the ionization produced by this electron. Then you have elastic scattering, which has a smaller cross-section, is a mixture of charged and neutral currents. And what you observe is the ionization produced by the electron in the target detector. Or you can have also other processes. For example, in the case we use heavy water as a target, one can consider interaction on deuteron, the charged current, and we observe the ionization of the electron, because the ionization of proton in water or in liquid scintillator is quenched in such a way that the amount of energy released is very small. Or through a neutral current where a neutron is produced and we observe the capture of neutron on hydrogen on the deuteron producing helium-3, or by adding chlorine, we can also observe harder gamma rays of the order of 8.6 MeV. So this was a great idea, exploited, as a matter of fact, as I will show you in CNO heavy water Cherenkov detector. So this is a list of past and present experiments, and this list goes over the last 56 years. With different techniques. The color code here, as a matter of fact, is the following. This light pink is the color referred to radiochemical experiments. In blue, you see the water Cherenkov detectors, and in orange, the liquid scintillator detectors. At the present time, only Super Kamiokande and SNO Plus are taking data on solar neutrinos. But we have had a long history, a fundamental history to understand also the neutrino properties besides the solar physics, which will be described later today. So the reactions exploited are these ones. And you see that in presence of chlorine, it was observed with this energy threshold, the radioactivity of argon-37. In case of gallium, with this lower threshold, the radioactivity of germanium-71. For elastic scattering, in principle, there is no threshold. It's only the ability of the detector which establish the detector threshold. And on heavy water, these two processes with a threshold of 1 or 2 MeV. There is also another process, which I will talk about later at the end of my talk, which is a capture on carbon-13. Producing nitrogen with some radioactivity. So you see that the different detection processes have different thresholds, and so one can probe different sources of solar neutrinos. The most are above 1 MeV. So this is the final results, if you want, in a nutshell, of 56 years of observations, where on the y-axis you see the ratio of the measurement to the solar standard model predictions, to the prediction, and on the x-axis the energy. So you can appreciate the fact that the most of the experimental results show a deficit with respect to the theory, with the exception of the neutral current measurement exploited by SNO water Cherenkov. So this is clearly understood as a flavor change in the solar neutrino sector, and it's a fundamental result today clearly interpreted in a theoretical framework. So before going into more details on the results, let me tell you about backgrounds. Okay, just a little bit. So the classification of radioisotopes in rare processes experiments dealing with solar neutrinos or double beta decay, dark matter, is the following. So there is a primordial long-lived isotopes, uranium, thorium, and they are belong to the natural radioactivity. Cosmogenic background produced by cosmic rays in our detector. And anthropogenic, produced by nuclear tests after the World War II, and they are propagating around, and they can contaminate, as indeed it's the fact, our detectors, in particular krypton 85. So when we deal with these radioactive elements, we have to understand that, for example, uranium-238 produces several decays. All of them are contaminating our detectors, 8 alpha decay, 6 beta decays. And this chain has also subchains which can be in equilibrium with the father. And in this case, we speak about secular equilibrium, or the chain can also be broken. So in that case, the activity along the chain can be different. And this is a crucial point. In addition, for uranium, there is radon, which is a noble gas, so can move around easily. And this noble gas produces a beta decay with many gamma rays contaminating our detector. Similar thing for the thorium chain, where you have 6 alpha decay, 4 beta decays. In addition, here there is thallium-208, which produces the hardest gamma ray from natural radioactivity. Okay, so in fact, all the beta decays with a Q value less than 2.6, they have troubles with this radioactivity. There is an important technique developed in particular in the framework of Borexino, exploited extensively, is the so-called BIPO tagging, where you detect a sequence of beta alpha decay correlated in space and time, and this allows to establish the radioactivity of with at the level of 10 to the minus 6 microbecquerel per kilogram, so a very, very low level of radioactivity. So if the chain is in equilibrium, then you can establish the radioactivity of the full set of decays. So let me spend a few words about SNO water Cherenkov. So this detector, I told you, was using heavy water, and actually was a breakthrough in the field. In fact, through the charged and neutral current, it was established the presence of flavor change processes in the sector of solar neutrinos. And in fact, here you see the flux of mu and tau neutrinos from charge current and elastic scattering. Charge current, you are sensitive only to electron neutrinos as a function of the flux of electron neutrinos. I think the first to highlight this point was Sergei Petkov in 2001, that before the neutral current measurement, this was already a significant observation of flavor change in the sector of solar neutrinos. When you add neutral current, the statistical significance increases a lot, and this is a fundamental result. So the important point is to establish that the flux of electron neutrino is not greater than the elastic scattering when using charge current, and in the case of neutral current can be as large as what you produce from the theory. Okay, now let's ask ourselves, how is it possible to measure sub-MeV solar neutrinos? So the point was faced in 1998, at the end of 90s last century. And the important observation is that due to the radioactivity in high purity water, so the high purity water can be purified at the best at the level of 10 to the minus 15, 14 gram of uranium thorium per gram of water. So with this level of radioactivity, we know that the detection threshold can be at most at the level of 3.5 MeV. And this is the case of Super Kamiokande after exploiting this technique over many, many years. So in order to go below this and be able to observe sub-MeV solar neutrinos, it was thought that the only way was to use an organic liquid scintillator, where the light yield is much higher, and so one can establish a lower detection threshold. But the point was that this detector is rich in hydrogen and electrons, so it's a good target. It consists of a solvent plus a solute, where the bulk is the solvent as a target. The solute is only used to enhance the light production due to scintillation. So the question was, the solvent must be very, very radiopure. How much the radiopurity we are talking about? This is easy to establish because if, for example, we aim to observe a beryllium-7 neutrino at about 0.9 MeV, this is the cross-section, elastic scattering. This is the flux we can take into account. And so for 100 tons of liquid scintillator, this is the case of Borexino, you have that many of electrons, and you expect 70 count per day. So this is easy to determine. So what about radioactivity? So if you assume 100% efficiency in pulse shape discrimination, namely in the ability to reject alpha background, and you allow this radio purity, then you have about the same number of expected events. So the signal to 1 is of the order 1. We want to have at most, I mean, at minimum, signal to noise of the order of 1. So the requirement is a radio purity equal or better than 10 to the minus 16. This means 10 to the minus 4 microbecquerel per kilogram. It's a very, very low level of radioactivity, which can be only measured with a tone scale detector. Otherwise, it's impossible. So this was the big challenge, to reach this low level of radioactivity to be able to perform this measurement. In addition to the background sources we have discussed, there are others, very important, because they can be inside the detector, and namely argon, krypton, lead, radon daughters. And as you can see, all these radioactivity isotopes, they produce background below 1 MeV, so they are crucial. So the detector not only has to look at low level of uranium and thorium, but also a very low level of these other isotopes. So this is the big challenge. So this was done in Borexino successfully. I don't want to discuss now in detail the detector. If you want, we can do it later. I assume this is known. So this was with a fiducial volume of the order of 100 ton with an active and passive shielding. And this is a picture of the field detector with liquid scintillator. What you can see is that this is about 14 meters in diameter, and the light can go through this length. And this is crucial because you want your target to be light transparent, not opaque, to really be able to detect over tens of, order of 10 meters, the light produced inside the target. Okay, this is the spectrum expected in a detector such as Borexino with irreducible backgrounds. For example, carbon-14, it's in the molecule itself, so it's irreducible. It can be reduced, as it was done, using this organic scintillator made from oil, because in oil you have aged carbon, and so the ratio between carbon-14 to carbon-12 can be even a million times smaller. And in fact, carbon-14 is limiting the sensitivity to PP neutrinos, which is this spectrum here. On the other hand, if you consider beryllium-7 neutrino being this monoenergetic flux of neutrinos, the kinematic says that you expect a threshold, and this is a clear signature of like a smoking gun for beryllium-7 neutrinos if the background is low enough. Then at higher energy, you have a carbon 11, which is a cosmogenic background, which is dominating the rate at the depth of Gran Sasso, because of course carbon 11 depends on the flux of muons in the underground. And as you can see, this is in purple is the CNO spectrum, and this is in light green is the PP spectrum. So they are completely overwhelmed by this carbon 11 contamination. So it's maybe impossible to measure them at the depth of Gran Sasso. So the Borexino operations went through three phases, and I want to highlight this because it's important for our conclusions. So the first phase was after the filling and initial purification. The second phase, after a second purification, which was crucial to reduce krypton 85, and at some extent also polonium-210. And the third phase with the thermal insulation phase, which allowed CNO sensitivity. So these three phases are important for what I'm going to tell you later. So this is the radio purity achieved in Borexino, which was much better than what we expected. And because of that, it was possible to enlarge the physics case of the detector beyond the initial beryllium-7 goal. So this is a data reduction example in Borexino. So you have the rodate, initial filtering, muon cut. Then powerful data reduction is applied by the fiducial volume cut. So when you see this spectrum, this resembles what we have observed before, we have discussed before, with only one exception. So here you see clearly the shoulder due to beryllium-7. So this is a smoking gun. You don't need to do any fit. It's clear a signal there. This is carbon 11. Which also it's clear that it's carbon 11. This peak was unexpected. So this is polonium-210, and this is completely out of equilibrium with the proxy, which is lead-210, because otherwise we would have had here a bismuth-210 spectrum completely overwhelming the beryllium-7 shoulder. So this is clear out of equilibrium. And we know that this is because of the chemistry of polonium. It's the same thing in SNO+, and will be the same thing in other detectors. It's a huge contamination. But we dealt with this pretty well. So another important feature of the Borexino data reduction is the so-called threefold coincidence tagging to reduce carbon 11. So the idea here is the following. This was initially due to Deutsch in our collaboration group. So you have a muon. The muon is going through the detector, and in 95% of the cases, the muon kicks a carbon 12 atom producing a free neutron, leaving a carbon 11 there. The neutron will be captured. The neutron will be captured by the detector in 300 microseconds, leaving the carbon 11 here to decay in half an hour. So one can tag the neutron capture because it emits a 2.2 MeV, and so you have a threefold correlation which allows to reduce the carbon 11 as you see in this spectrum. So reduction of carbon 11 allowed us to simultaneously study PP beryllium-7 and PP neutrinos. And this was very important to determine some fundamental parameter of the solar neutrino physics and probe the PP chain. This was done. This is an important result to the ratio of the termination 1 and 2 in the PP chain, which I think can be further detailed by Francesco today. So going to the challenge for CNO solar neutrinos. So here you see the spectrum. This is in red is the CNO spectrum. This in blue is the dotted, is the bismuth coming from lead to 10. And there is in the region of interest, a clear degeneracy between these two spectra. Therefore, in order to really perform a spectral fit here, we need to understand the amount of contamination due to bismuth to 10, which depends on lead. So the lead produces bismuth, which is a beta decay, and polonium, which is alpha decay. Polonium is the huge peak that we have seen before. So in order to do that, we made the following reasoning. The polonium, which is out of equilibrium and which we see inside the detector, is not supported by lead. So the scintillator has a bulk contamination of lead, which produces bismuth supported by lead inside the liquid scintillator and produces also some polonium supported by lead. There is extra polonium not supported coming from the inner vessel. Okay? So if we have convection currents inside the liquid scintillator, this polonium can migrate and contaminate the fiducial volume. And this was indeed the case. And in order to reduce these convection currents, we thought to install a thermal insulation system, passive and active, in order to establish a strong and stable gradient of temperature and dump completely, or almost completely, the convection currents inside due to seasonal variations. In the end, we succeeded to have a seasonal variation of the order of 0.1 Celsius inside the fiducial volume. So this dump of the convection current produced this effect. This is polonium to 10, because polonium to 10 can be easily measured through pole shape discrimination. And if we know polonium to 10 supported, we also know bismuth to 10 supported inside the core of the detector. So here you see that before the thermal insulation system, this was produced, it's polonium to 10 in the fiducial volume, fluctuating due to the convection currents. When the thermal insulation was set at work, then you have a reduction of the contamination and a stable detector. In this way, we could constrain the bismuth to 10 inside the fiducial volume at 11 counts in 100 tons. So doing that, you can apply this to the spectral fit and be sensitive to CNO neutrinos. And in fact, the only constraints we applied to the spectral fit were the bismuth constraints, plus the assuming that the PP neutrino flux, and namely the rate, was constrained to the PP luminosity. Okay, and this is because the sun is shining and we have measured at 10% PP neutrinos. So this is the constraint is from the prediction of the solar model, which for PP neutrinos we think is very robust. So in this way, the null hypothesis was rejected at 5 sigma in the initial measurement of CNO neutrinos. So this is was the first spectral measurement of CNO neutrinos, using data from the third phase. But we did more, considering that, okay, maybe this, if you are not really focusing on this beryllium constraint, you can think, okay, this is a weak assumption. And for that, we used the Cherenkov versus scintillation property in a liquid scintillator. Cherenkov light is produced very fast, picoseconds, and it's directional. Scintillation light is produced with a decay time of the order of a few 10 nanoseconds, and it's isotropic. So one can build PDF from Monte Carlo to really simulate this and predict this feature of a scintillation light produced. And this was done and tested with beryllium-7 neutrinos. So beryllium-7, you really know these are the beryllium-7 neutrinos. So we apply a region of interest around the shoulder of beryllium-7 neutrino, and we probe this effect. And this effect was successfully probed because you can correlate the direction of the sun with the first PMT's heats. Then this idea was applied to CNO neutrinos and was successfully successful because in the end we could measure CNO neutrinos in a region of interest where the dominant neutrino flux is due to CNO neutrinos by using, you know, the first, when a neutrino interacts in the detector, the first, it's the Cherenkov light is produced in the direction of the event and with respect to the sun, which we know for each event. And the first PMTs hit by the light are with a high probability hit by Cherenkov light. So this was used in a multivariate log likelihood fit to determine at high significance the CNO rate. So in the end, CNO rate was measured through bismuth-constrained directionality and with a combined analysis at a sigma significance. So I think we can consider this a robust result. So these are the results from Borexino, the different fluxes. I leave it there for you to look. Let me just finish my talk saying a few words about SNO+. SNO+ is in data taking since 2023. They have not a great exposure at the present time. They use 780 ton of LAB scintillator, the same scintillator which is going to be used by Juno. And so far, they have done interesting measurements on solar neutrinos. I'm not talking about geoneutrino or reactor neutrinos. This is a Boro 8 measurement of the solar neutrinos. But in addition, they have also probed this interaction channel that Francesco Villante, Daniele Montanini, and myself developed in a paper in 2005. This carbon-13 charge current interaction, they have observed with a poor statistics at present, but it's a clear signal already there. And this it's because carbon-13 is only 1% isotopic abundance, but provides a very strong signature. And for future large detectors, such as Thea, for example, is one of the interaction channels taken into account. So, in conclusion, let me say that after 56 years, because the Homestake started in 1968, solar neutrino observations have been very successful. Fundamental results achieved on neutrino physics and astrophysics. More to come with Super Kamiokande SNO+, although SNO+, maybe in a couple of years will turn to double beta decay measurements. And future observations with Hyper Kamiokande, Dune, and Juno. But what I'd like to highlight today is that last week, we had the first results from Xenon, Anton, and Panda X at Gran Sasso and Jinping, respectively, about solar neutrino from Boro 8 measured at 2.6, 2.7 significance level, sigma, or through neutrino nucleus coherent scattering. So this is the first example. You know that this dark matter experiment have been advocating the possibility to use coherent scattering to probe solar neutrinos. They have started doing that. I think it's clear that this process has been measured. So we know that the neutrino nucleus coherent scattering has been measured. It's more or less what we expected. These neutrinos from the sun are there. We don't know about dark matter, but these neutrinos are there. So if the collaboration is smart enough, they can take it out from the background, and in fact, they did it. So thank you for your attention.
So, congratulations.
So if you have questions, I can explain more technical
Francesco.
details.
I have two comments. I apologize because they're personal comments. And But since you are very careful to describe also how ideas came out, let me say that you forgot to mention that two things. The first one is that you forgot to mention that the idea to use polonium in order to trace bismuth was proposed in a paper that we wrote together also with Francesco and Giulia, which actually triggered the formation of the CNO working group. Following this approach, it was shown that it was necessary to insulate the detector, and then all the story, the successful story of Borexino. The other historical remark is the fact that you are right that the first model-independent evidence for solar neutrino oscillation was obtained in 2001 by comparing the snow-charged current measurement with the Super Kamiokande result. This was done by matching the response function of the two detectors by applying an approach that it was produced in 98, proposed in 98 by myself. I was a PhD student, as it is also acknowledged in the paper of the SNO collaboration.
Thank you, Francesco, for this. Last night, actually, I thought I should have mentioned this paper. It's also, I'm signing that paper too. But I already sent the slides. We can for sure update. Indeed, there was this paper by you, myself, and others where we proposed to use the tagging of polonium for CNO measurements, as a matter of fact. This is true, yes. Actually, personally, I'm very proud of this study that we did, because in the end, this was exploited and worked. To use this constraint to determine the CNO neutrinos. The other point, yes, I'm very well aware of this paper. I just wanted to highlight that the charged current before the neutral current came in were already enough to significantly measure the flavor change. Thank you for the comments.
Thanks for the talk. Just one question. Can you a bit more on the gallium measurement?
On the, sorry?
Gallium experiment to measure solar neutrinos.
Gallium. Gallium. Yeah, gallium. So yes, the gallium experiment was. Let me go to this. Was in the line of the chlorine Homestake experiment using chlorine here, was using gallium. Okay, in Gran Sasso in a liquid solution, and metal gallium in Baksan, the SAGE experiment. This was, what happened is that through this channel you produce germanium-71. Then and you let the detector sitting, absorbing solar neutrinos for 20 days. At that point you purge the volume with nitrogen several times to collect this germanium is in a volatile compound inside the gallium solution, and this volatile compound pushed by the nitrogen, on the contrary in chlorine they used helium, is pushed in a charcoal where it's essentially is frozen, and then taken into a low radioactivity counter. At that point, this concentrated solution with germanium produced by solar neutrino is counted in a proportional counter with very low background for several months. And you see the decay of the germanium-71 producing X-rays, and from that you extract the solar neutrino rate. Production rate. The same technique was applied for similar technique for chlorine. Oh yeah. This was also an important measurement because the most of the signal was due to PP neutrino. So this was the first hint of PP neutrino flux. But in the end, In the global fit, all the measurements from the different experiments are combined together. So it's, of course, they are taken into account. It's.
Okay, thank you.
Okay, it's okay. Okay, actually, I have two questions. One is an experimental one. So now you have the fantastic CNO measurement, but what's the future? Is there any other experiment worldwide or in the foreseeable future improving on this?
I don't know. I think it's difficult because in SNO Plus there is a huge amount of polonium, so I think that for them it will be difficult to go around 1 MeV sensitivity. And in addition, they are not planning to go through this because they are focusing on double beta decay with tellurium. They consider that a more fundamental measurement to be done. In other cases, I think it's. I don't see a project at the present time which will do this.
Okay. My other question was maybe to somebody else. So there's this thing about the high Z and low Z solar models, right? Which you can distinguish, and then it's that all questions seem solved potentially by there was paper by Ranelli and collaborators about having new measurement or something. So is that resolved now? Do we know from a solar model perspective which is the correct model, or is there still does this problem still exist?
Well, I leave this floor to Francesco. He will discuss in the afternoon about that.
Yes, I think that the situation is still not solved in this. Yes. No. Okay.
But what I want to what I want to Rafael, I want to underline is that SNO Plus indeed has a great opportunity to do that because they are very deep. And so the carbon 11 at SNO lab depth is much reduced. So they have much less of a problem with respect to Borexino. So if in the future, for example, I don't think this will happen at SNO lab, but maybe in Jinping, if there will be a new experiments in this kind, the depth of Jinping is similar to SNO lab, so maybe they can be done.
Which are deeper than Borexino. And the larger in mass could compensate with the statistic and with the fact that the cosmogenic background is lower, the fact that maybe they are not as clean as Borexino, because Borexino made several world records of purity, which are very difficult to be reproduced in other experiments.
Well, I think maybe SNO lab they can, with some effort, they could do it, but it's not in their plan. So in the horizon, I don't see an opportunity.
Can you show the 14? Slide number 14. I think. No, this one, 13.
13. Okay.
Yes. So what I see, the PP. Now in gallium experiments, there is a contribution from PP. There is a 30% contribution from beryllium. And there is about 8-10% contribution from boron neutrinos. Now, however, the Borexino PP is a pure PP, and I see that there is some kind of a difference between the two. I would expect the gallium result to be on the top of Borexino result for PP, to be larger than the, maybe I'm wrong. You understand what I mean?
Yeah, this is... I think here, because this is elastic scattering, it's the ways that the ratio of the observed rate is a mixture in this case. So there is some contribution of elastic scattering, neutral current, and so this is going a bit higher than gallium, where it's only electroneutrinos. I think the difference is due to this. So because also in Homestake, the most of the signal, I think, is from beryllium-7.
No, Homestake, the most of the signal is from boron neutrinos, And then there
there
is a contribution from beryllium and a little bit of the rest. But mostly it is boron neutrinos.
Yes, no, correct, yes. So I think the difference is because of that. The ratio, because this is the measured, just the observed ratio without any filtering from flavor change.
Since I saw the photo, there are many photos in this building, historical photos. There is a photo of Pontecorvo with Bilinchi. So this reminds me that actually the radiochemical methods of neutrino detection were proposed by Pontecorvo, and in particular the chlorine-argon reaction used in the Homestake experiment was proposed by him in 1946.
Yeah, I've seen that picture walking in. Yeah, in fact, this is a good point also because the Homestake technique and the account of all the backgrounds was taken by Ray Davis from a paper from a very detailed, comprehensive paper by Luis Alvarez, I think 1949. But also Luis Alvarez took the idea from Pontecorvo about the interaction channel.
As far as I know, Pontecorvo developed even the proportional counters that were used by Davis later, I mean, the version, and also in gallium-germanium experiment. So he was working...
No, it was Pontecorvo together with Luis Alvarez, I think, were the pioneers in this.
In Alvarez's paper, he quotes Pontecorvo paper, and
yes, yeah.
And actually, there is a statement that the only thing that can work, the chlorine-argon method, was proposed by Pontecorvo. It's a very clear statement about it.
No, yes, I remember that. I just want to say that Alvarez was really detailed on all the background sources, and I think this was crucial for Davis to develop the Homestake.
Now, a comment from Cristina Volpe, but before I would like to subscribe the point of Sergei. While in the case of Borexino, you can declare the energy at which you have the measurement, in the gallium and the Homestake case, I mean, you cannot, basically. So somehow this is how can I say, is very kind toward the gallium and Homestake measurement for what concerns the horizontal scale, in my view. I mean, this we can say now. At the time, we could not. Yeah.
No, I agree. There is no, here in this case, there should be, but also a little bit for Borexino, but there should be a wide horizontal error bar. This is taken on the average, folded with the energy spectrum response, yes.
Okay, so I would like to come to one of the last slides where you showed this signal from on carbon-13, neutrino on carbon-13. One of the very last. Okay, my question is the following. Already neutrino on carbon-12, the prediction of the cross-section can be off by a factor of 2 if one doesn't put the correct correlations into the matrix elements for this process. Now, carbon-13 is even more difficult because it's not an even, but it's an even-odd nucleus. However, nowadays with the ab initio calculations, for example, shell model, we can calculate very well these light nuclei. So my question is, in this result that you showed, the neutrino carbon-13 cross-section, how, I mean, it's just a few MeV, so we know how to treat it. However, if we don't treat it well, it can be completely off. So I would like to know what kind of input has been put in this result.
So this, the carbon-13 cross-section, to my knowledge, is to the ground state, because the consideration is that this goes to the ground state.
Yeah, the exclusive.
It's well measured because the FT factor, the half-life is well measured. So we used that information.
So you use that. Okay, very good.
Can I ask also, sorry, how did the dark matter colleagues assure that they're seeing solar neutrinos?
Okay, well, this is a good point. So I just heard about this analysis a few days ago, but the understanding is the following, that they know what is the, more or less the expected signal. So they build probability density function of the response of the detector for nuclear recoils, over taking into account in the specific energy window where this signal is expected to be, and taking into account other sources of accidental backgrounds and so on in the nuclear recoil response, and perform a spectral fit, a fit. So it, in the end, it's a subtraction, the final analysis. The same thing they aim to do on electron recoils, for, in particular for the xenon, for PP neutrinos. Because for PP neutrinos, they are sensitive to PP neutrinos if they are able at some point to subtract properly the electron recoil background due to radon mainly.
Do you know how many events they have or something? And what do they subtract?
10 events in the end, candidates. Order of 10 events, if I remember. 10 events, you were there. And the statistical significance they claim is 2.7 sigma.
Anyway.
But this is, maybe the limitation of the analysis is that, but it's...
So we can continue the discussion at the coffee break. I propose to take again.
Thank you.